There are many instances in programming where we need more than one variable in order to represent an object. For example, to represent yourself, you might want to store your name, your birthday, your height, your weight, or any other number of characteristics about yourself. You could do so like this. Std string my name. Int my birth year. Int my birth month. Int my birthday. Int my height inches. Int my weight pounds. However, you now have 6 independent variables that are not grouped in any way. If you wanted to pass information about yourself to a function, you'd have to pass each variable individually. Furthermore, if you wanted to store information about someone else, you'd have to declare 6 more variables for each additional person. As you can see, this can quickly get out of control. Fortunately, C++ allows us to create our own user-defined aggregate data types. An aggregate data type is a data type that groups multiple individual variables together. One of the simplest aggregate data types is the struct. A struct, short for structure, allows us to group variables of mixed data types together into a single unit. Because structs are user-defined, we first have to tell the compiler what our struct looks like before we can begin using it. To do this, we declare our struct using the struct keyword. Here is an example of a struct declaration. Struct employee. Short ID. Int age. Double wage. This tells the compiler that we are defining a struct named employee. The employee struct contains 3 variables inside of it, a short named ID, an int named age, and a double named wage. These variables that are part of the struct are called members, or fields. Keep in mind that employee is just a declaration. Even though we are telling the compiler that the struct will have member variables, no memory is allocated at this time. By convention, struct names start with a capital letter to distinguish them from variable names. When we define a variable such as employee Joe, Joe refers to the entire struct, which contains the member variables. In order to access the individual members, we use the member selection operator, which is a period. Here is an example of using the member selection operator to initialize each member variable. Employee Joe, create an employee struct for Joe. Joe.id equals 14, assign a value to member ID within struct Joe. Joe.age equals 32, assign a value to member age within struct Joe. Joe.wage equals 24.15, assign a value to member wage within struct Joe. Employee Frank, create an employee struct for Frank. Frank.id equals 15, assign a value to member ID within struct Frank. Frank.age equals 28, assign a value to member age within struct Frank. Frank.wage equals 18.27, assign a value to member wage within struct Frank. Struct member variables act just like normal variables, so it is possible to do normal operations on them. Int total age equals Joe.age plus Frank.age. If Joe.wage Frank.wage. Std could Joe makes more than Frank \n. Else if Joe.wage. Std could Joe makes less than Frank \n. Else Std could Joe and Frank make the same amount \n. Initializing structs by assigning values member by member is a little cumbersome, so C++ supports a faster way to initialize structs using an initializer list. This allows you to initialize some or all the members of a struct at declaration time. Struct employee. Short ID. Int age. Double wage. Employee Joe equals 1, 32, 60,000.0, Joe.id equals 1, Joe.age equals 32, Joe.wage equals 60,000.0. Employee Frank equals 2, 28, Frank.id equals 2, Frank.age equals 28, Frank.wage equals 0.0, default initialization. It is common to have either a pointer or a reference to a struct, or class. As you learned previously, you can select the member of a struct using the member selection operator, dot. Struct person. Int age. Double weight. Person. Member selection using pointer to struct. Person asterisk ptr equals end person. Asterisk ptr, dot age equals 5. Because the syntax for access to structs and class members through a pointer is awkward, C++ offers a second member selection operator, dash, for doing member selection from pointers. The following two lines are equivalent. Asterisk ptr, dot age equals 5. Ptr dash age equals 5. In the past, memory was extremely expensive, and computers did not have much of it. Consequently, there were incentives to make use of every bit of memory available. Consider the bool data type. Even though it only has two possible values, true and false, which can be represented by a single bit, it takes up an entire byte of memory. This is because variables need unique addresses, and memory can only be addressed in bytes. The bool uses 1 bit and the other 7 go to waste. Using bitwise operators, it is possible to write functions that allow us to compact 8 booleans into a single byte-sized variable, enabling significant memory savings at the expense of more complex code. In the past, this was a good trade-off. The bitwise left shift. The left operand is the expression to shift, and the right operand is an integer number of bits to shift by. So when we say 3, for example, consider the number 3, which is binary 0011. 31 equals 0110 equals 6. 32 equals 1100 equals 12. Note that in the third case, we shifted a bit off the end of the number. Bits that are shifted off the end of the binary number are lost forever. Reminder, we're working with 4-bit values here. With an 8-bit value, 3. In this case, the 4th bit wouldn't be shifted off the left end of the binary number. The bitwise right shift operator shifts bits to the right. 12.1 equals 0110 equals 6. 12.2 equals 0011 equals 3. Note that in the third case we shifted a bit off the right end of the number, so it is lost. Although our examples above involve shifting literals, you can shift variables as well. Unsigned int x equals 4. X equals x. The bitwise NOT operator is perhaps the easiest to understand of all the bitwise operators. It simply flips each bit from a 0 to a 1, or vice versa. Note that the result of a bitwise NOT is dependent on what size your data type is. Assuming 4 bits. 4 equals 1011 equals 11, decimal. Assuming 8 bits. 4 equals 1111. 1011 equals 251, decimal. Bitwise N, and bitwise OR, work similarly to their logical and logical OR counterparts. However, rather than evaluating a single Boolean value, they are applied to each bit. For example, consider the expression 5-6. In binary, this is represented as 010101110. To do any bitwise operations, it is easiest to line the two operands up like this: 01106, and then apply the operation to each column of bits. If you remember, logical OR evaluates to true, 1, if either the left or the right or both operands are true, 1. Bitwise OR evaluates to 1 if either bit, or both, is 1. Consequently, 5-6 evaluates like this: 01106, 01117. We can do the same thing to compound OR expressions, such as 146. If any of the bits in a column are 1, the result of that column is 1. 01004, 01106, 01117, bitwise N works similarly. Logical N evaluates to true if both the left and right operand evaluate to true. Bitwise N evaluates to true only if both bits in the column are 1. Consider the expression 5 and 6. Lining each of the bits up and applying an operation to each column of bits. The last operator is the bitwise XOR, caret, also known as exclusive OR. When evaluating two operands, XOR evaluates to true, 1, if one and only one of its operands is true, 1. If neither or both are true, it evaluates to 0. Consider the expression 6 cubed. The smallest addressable unit of memory is a byte. Since all variables need to have unique addresses, this means variables must be at least 1 byte in size. For most variable types, this is fine. However, for Boolean values, this is a bit wasteful. Boolean types only have two states, true, 1, or false, 0. This only requires 1 bit to store. However, if a variable must be at least a byte, and a byte is typically 8 bits, that means a Boolean is using 1 bit and leaving the other 7 unused. In the majority of cases, this is fine. We're usually not so hard up for memory that we need to care about 7 wasted bits. However, in some storage-intensive cases, it can be useful to pack 8 individual Boolean values into a single byte for storage efficiency purposes. This is done by using the bitwise operators to set, clear, and query individual bits in a byte, treating each as a separate Boolean value. These individual bits are called bit flags. When talking about individual bits, we typically count from right to left, starting with 0, not 1. So given the bit pattern 000001111, bits 0 through 2 are 1, and bits 3 through 7 are 0. In order to work with individual bits, we need to have a way to identify the individual bits within a byte, so we can manipulate those bits, turn them on and off. This is typically done by defining a symbolic constant to give a meaningful name to each bit used. The symbolic constant is given a value that represents that bit. Define 8 separate bit flags. These can represent whatever you want. Const unsigned char option 0 equals 0b000000001, represents bit 0. Const unsigned char option 1 equals 0b000000010, represents bit 1. Const unsigned char option 2 equals 0. Const unsigned char option 7 equals 0b100000, represents bit 7. The next thing we need is a variable that we want to manipulate. Typically, we use an unsigned integer of the appropriate size, 8 bits, 16 bits, 32 bits, etc. depending on how many options we have. Since we have 8 options above, we'll use an 8-bit value to hold our options. Each bit in miflix corresponds to one of the options defined above. Unsigned char miflix equals 0, all bits turned off to start. To set a bit, turn on, we use bitwise or equals, operator, smiley face. Miflix equals option 4, turn option 4 on. Let's unpack this one to show how it works in more detail. Miflix equals option 4 is the equivalent of miflix equals, miflix option 4. Evaluating the portion between the parentheses. Miflix equals 0,000,000,000, we initialized this to 0. Option 4 equals 0,000,100,000. Result equals 0,000,100,000. We can also turn on multiple bits at the same time using bitwise or. Miflix equals, option 4 option 5, turn options 4 and 5 on at the same time. To clear a bit, turn off, we use bitwise and with an inverse bit pattern. Miflix and equals option 4, turn option 4 off. Let's say miflix was initially set to 0,000,100, options 2, 3, and 4 turned on. Miflix and equals option 4, is the equivalent of miflix equals, miflix and option 4. Miflix equals 0,000,100. Option 4 equals 1110 1111. Result equals 0,000,1100. To query a bit state, we use bitwise n. If miflix and option 4 std could miflix has option 4 set. If miflix and option 5 std could miflix does not have option 5 set.